All right, so chapter 5, we are starting to talk about things that are non-linear. So we are going to start looking at things that do not form nice straight lines. So far, we've only talked about linear families, multiple representations. We've talked about tables, graphs, equations, and in this chapter, we are going to start talking about things that are exponential functions and the type of growth that models. In the book Mice and Men by John Steinbeck, two good friends named Lenny and George dream of raising rabbits and living off the land. What if their dream came true? Suppose Lenny and George started with 2 rabbits, and during the first month, those rabbits have 2 babies. Also suppose that every month thereafter, each pair of rabbits has 2 babies. How many rabbits would Lenny and Squiggy how many rabbits Lenny and Squiggy would have after 1 year? Definitely poor wording on my part. So we would want to just sort of make a guess there. That's not a question where I expect you to know the answer. You'd want to make an estimate. Okay, so this is going to be different from everyone, and you would make your own guess. So just sort of think about it for a second. How many do you think they'd have at the end of the year? State the assumptions you made when you modeled the number of rabbits raised. So one assumption is that all rabbits reproduce exactly once per month. And we're also going to talk that every rabbit is healthy and they're all male-female pairs, that we consistently have the same number of males and females. So there's not a concern about there being any rabbits not being able to reproduce. Now, I understand this is kind of weird, but just run with me on this one. How can you determine the number of rabbits that will exist at the end of 1 year? Consider this question as you work through the problems below. Draw a diagram to represent how the total number of rabbits is growing each month. All right, so what I would start with is on month 0, we have a male-female pair. Okay, so at month 0, we have 2 rabbits. Okay, then at the end of 1 month, there is a new male-female pair. So at the end of month 0, there were 2 rabbits. At the end of 1 month, we have 4 rabbits, right? We have the 2 we started with plus the 2 new ones. Now, each month, each pair has another pair of babies. So this one in month 2 would have another male-female pair. This one in month 2 would have another male-female pair, bringing us to 1, 2, 3, 4, 5, 6, 7, 8 rabbits total at the end of 2 months. Now, it gets a little tricky to show this just because of space, but the next one would be month 3, right? And so in month 3, this pair would have a new male-female pair. This pair would have a new male-female pair. This pair would have a new male-female pair. And this pair would have a new male-female pair. So at the end of 3 months, we would be up to 16 rabbits. Now, at this point, you probably don't need to make any more of the diagram. You're going to say, oh, look, 2, 4, 8, 16, we're multiplying by 2. So this would be 2 to the first, this would be 2 to the second, this would be 2 to the third, this would be 2 to the fourth, and so on. So you could fill in this table without having to continue the diagram by following the pattern. So 16, 32, 64, 128, 256, 512, 1024, and 4096. Now the question, I missed one. I definitely missed one. 512, 1024, right here. 2048, and then 4096. So the question becomes, how do we determine after n numbers of months? So we're just sort of looking at a year, which is why we stopped at 11, because month 0 would actually be January, and then February, and then March. So by the time you get to 11, that's actually December. Month n, these are all 2 to a power, right? But this isn't 2 to the 0, it's 2 to the 1. This isn't 2 to the 1, it's 2 to the second. The exponent is 1 higher than the month that we're in. So it would be 2 to the n plus 1, because our exponent value is 1 higher than the month we're in. The month we're in is going to be our n, what's considered our n value, and that's why at the bottom here we're saying, well, what's the rule for n? What's the rule for, say, 23 months from now? And we could do 2 to the 23 plus 1, and we do 2 to the 24th and get an answer. Now, on your graphing calculators, it is something you're going to need to be able to do are other exponents. So if we wanted 2 to the 24th, You would hit the 2 key, but then right underneath where it says clear, there's this little up key that's called a caret. Directly under the word key, clear, you're going to press the caret, and notice that it makes it look like a little exponent. So you could do 2 to the 24th, and you would hit enter, and you would get a rather large number. Now, let's say we're going to do something like 2 to the 100th, and now you get an answer like that, and you're like, whoa, what's with the E? Last year in MSM3, we talked about how sometimes an answer can be so big that the calculator can't show it on the screen, and they have to resort to scientific notation. So this would be 1.26, etc., times 10 to the 30th. And you could round it as such. If you needed 2 to the 100th, you could say it was approximately 1.2, that 6 we would round to a 7, times 10 to the 30th from the calculator, and work with that number. It's going to be a little bit off because we rounded it, but you do at some point have to say, hey, my calculator's just not big enough to show that on the screen. All right, so let's look at the back, and we're going to look at some other exponential patterns that show up a little differently. What patterns can you find in your table? Describe the pattern of the growth in words. What we found was that it was doubling. Ooh, not going to fit in there. The growth pattern grows by a constant amount, but it's growing by multiplication instead of addition. So growth is constant by multiplication instead of addition. And that's what makes it exponential. That's what makes it nonlinear. When we were going plus 7, plus 7, plus 7, or minus 2, minus 2, minus 2, we had a nice straight line, right? Because we'd go over 1, up 7, over 1, up 7. Well, now we're going to go over 1, up 2, over 1, up 4, over 1, up 8. And we're changing that slope. Determine the number of rabbits that Lenny and George would have after 1 year has passed. Now, depending on who you ask, if you're talking about 12, getting to the 12th term, if you're talking about n equaling 12, then it is 8,192. But if you're talking about getting to December, it's what we had on the table before, the answer that was in the 4,000s. Lenny and George want to raise as many rabbits as possible, so they have a few options to consider. They could start with a larger number of rabbits, or they could raise a breed of rabbits that reproduces faster. How do you think each of these options would change the pattern of growth you observed in the problem 5-1? Which situation will yield the largest rabbit population after 1 year? Now, this kind of question is much more useful for, say, somebody who owns a farm, and they want to say, like, do I need to plant more of this, or do I need to buy a variety that grows more on fewer plants? But this case comes from a real book, so we're going to use this one. Case 2, right? Because case 1 was on the front. Start with 10 rabbits. Okay, so at month 0, we have 10 rabbits. Each pair has 2 babies per month. So the 10 rabbits would become 20 rabbits at the end of month 1, would become 40 rabbits at the end of month 2, would become 80 rabbits at the end of month 3, and so on. This is the same concept as we had on the front, right? This is doubling. So that by the time we get down here to the 12th, we have 40,960 rabbits. That's with the doubling. Case 3, you start with 2 rabbits, and each pair has 4 babies each month. So these 2 have an additional 4 each. Does that make sense? The 2 rabbits have 4 new babies. So after month 1, you'd get 6. The 6 babies, or the 6 rabbits, have 12 new babies, making it 18 at the end of the next month. At the end of the next month, the 18 have 36 new babies, making it 54. So what's happening in this one is you are having twice as many babies as you had pairs or a number of rabbits before. So we had 6 rabbits. That's 3 pairs. Each of the 3 pairs is having 6 pairs. So 3 pairs of rabbits is 6. 6 pairs of rabbits is 12. Add them together, we get the 18. 18 is 9 pairs of rabbits having 18 pairs of rabbits. So 9 pairs is 18, 18 pairs is 36, add it together for 54. By the time we get down to month 12, that is 1,062,882. Whoa. Okay. And then in case 4, it says Start with 2 rabbits. Each pair has 6 babies per month. Well, clearly that is following the same pattern as case 3. At month 0, we have 2 rabbits. Well, each of them has 6. So in month 1, we would have 8. Of those 8, if I add in, now 8 is 4 pairs, they're going to each have 3 pairs, which would be 24 new rabbits. Yeah. Wow. And that means at month 2, we would have 32 total. The next one, if we got 3 months, we have 32 babies. Let's see. We would have 96 new. Wow, geez, it's 3 new pairs per pair. So that gets us up to 128. And if you follow that pattern, by the time you get to month 12, you have 33,552,432. So in which case will Lenny and George have the most rabbits? It's case 4. And how many will they have? That is the 33,552,432. So it's not the starting value that gets you to a higher number, right? Here we started with 10, but since they were each only having 2, it didn't grow as fast. Here, when they were each having 4 babies, grew faster. Here, when they were each having 6 babies, grew faster. So you will notice that the numbers that we're adding are going up by more quicker. Look back at the tables you created in the previous problems. What pattern do they all have in common? Their growth pattern is multiplication. So growth is multiplication. And what do we mean by that? In the first one, we were just doing times 2, right? Times 2, times 2, times 2. In the second one, it's times 3, times 3, times 3. Notice we started with a different value, though, so it took a second to catch up. But in the very next round, case 3 would have beaten case 2. In this one, because we're having 6 new babies per month, that means that we're actually doing times 4 because you're including the previous ones as well. So their patterns are patterns of multiplication. All right. Graph the data for case 2. What is the general shape of the graph? So if we graph the data for case 2, it is a curved pattern. And think about what I said before about slope, how we're going over 1 up 10, and then over 1 up 20, and then over 1 up 40. So if we want to look at the curve for that, after 1 month, we would have 20. So 20 would be right there. At 0 months, we had 10. After 2 months, we have 40. After 3 months, we have 80. And then after 4 months, we would have had 160. And so we get this curved pattern. All right. And let's see. Graph the case general shape, curved. From left to right, is it increasing or decreasing? So as I go from the left and I move to the right, it's going up, so it is increasing. If you drew a line or curve through the points and extended the graph in both directions, what would be the x-intercept if possible? So this graph is never going to touch the x-axis. If we kept going down, 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 further to the left, it's always going to approach the x-axis, but it's never going to touch the x-axis. So we would say that there is no x-intercept. The y-intercept is 10, 0, 10. At 0 months, we had 10 rabbits to start with. Are there any values of x or y which are not possible in the function? We can't have any negative values. Nothing goes into the negative quadrants. We can't have negative numbers of rabbits. So there are no negative values. What is the domain and range of the graph? So the domain, right? Domain is side to side. It goes from 0 to infinity because our first point starts here at 0 and goes on and on and on forever. So 0 to infinity. And our range, the lowest point is 10, and then it goes on forever. So 10 to infinity. And we know this isn't perfect. We know it's not actually going to go on to infinity. There's going to come a point where rabbits start to die and it starts to flatline. But we're considering this as sort of a general case. Is it continuous or discrete? Now, technically it is discrete because we are counting rabbits. We don't have decimals and we're not measuring anything. So no decimals and we are measuring, we are not measuring, that makes it discrete. I did draw in my curve just so you could see that it was a curved function. Technically, there should be no curve. It should just be dots. So dots only for discrete. And is it a function? Absolutely. Passes the vertical line test. One and only one answer for any value of x. All right, so this one's a lot to take in. And there are some questions that we can go over on the homework that have to do with these patterns. But what I suggest is that you can always go back and draw your pattern to start. So for example, this is my sort of fancy looking version where I had it on the computer. And I color coded it. I labeled it month 1, month 2, month 3. There are also options for doing, the graph, where the graph is always going to be helpful so you can look at things. And now you guys are at a point where you can use your graphing calculator occasionally to assist as well. So don't forget about what I said about how to do exponents. See you in class.